Swayam Prabha. Digital India. Educated India.
Hi, and welcome to Lecture 11 on Computer-Aided Engineering Design. This lecture is about viewing of solids. Why do we need viewing? We are looking for a proper representation to comprehend a solid and to communicate an engineering design. Also, we would be interested in visualizing the making of a component in different views. Let me explain what I mean here. Imagine I'm trying to design a very complex component represented by this block. What you see would be this portion in the workspace. You would not have any idea about this vertex which is hidden. Say you would want to change the features around this vertex here, which is at the back side of the block. What you would want to do is you would want to rotate or reposition or reorient this component appropriately so that this vertex becomes visible to you. Once this portion is visible, you can perform any desirable feature modification here. To be able to do that, you are viewing this component in different ways. Again, in the process, you are doing nothing but reorienting. In the workspace, however, you will be seeing only the two-dimensional picture of this component. We'll talk about different aspects of viewing in this lecture. Views are of two kinds, parallel and perspective. Let's take the perspective views first. Let's start with a three-dimensional Cartesian space. The axes are marked here, and so is the origin. Consider any point P with coordinates x, y, and z. Let's drop a perpendicular or a projection line on the xy plane. The projector hits the xy plane at point P star. From this point, let's draw projections parallel to the x and y axes. Let's also nomenclate the points of intersection as A and C. Let us go down along the negative z direction and place our I point or R cells at a distance W from the origin. So E is our I position with coordinates 0, 0, and minus W. Next, we join the points EP. The essential idea is to view the perspective of point P on the xy plane as seen by the eye E. In other words, you would like to know how this point P star is positioned on the xy plane. P star is the perspective image of point P. Let's continue with the construction. We draw two projectors along or parallel to the x and the y axes, and we nomenclate the points, the intersecting points P and D. Next, we join the points O, P star, and P prime. It is the construction process that would make these 3 points collinear. Using this construction, we find the triangles P star, O, E and P star, P prime, P are similar triangles. Noting that, we see that the length ratios are equal. In other words, OE, which is this vertical height, over PP prime, which is this distance, the Z projection of point P, is equal to OP star, which is this distance, over P star P prime, and that is this distance here, is also equal to the modulus of EP star, or the distance EP star, this distance here, over P star P, which is this distance here. Note that distance OE is W and distance PP prime is Z. So using this component of equation and this component of equation, we rewrite EP star as W over Z P star P. W over Z P star P. Now this equation relates only the distances or moduli of EP star and P star P. But note from the figure that EP star is collinear with P star P. They have the same direction. With that said, I can relax the modulus sign here and I can rewrite the equation as EP star, the vector, equals W over Z, which is a scalar, times P star P, another vector. In other words, the vector EP star is a scalar multiple of vector P star P. Like I said before, we are interested in the coordinates of P star, the perspective image of P. Using vector algebra, we can say that OP star equals OE plus EP star. This is using the triangle law. OP star equals OE plus EP star. OE would be minus of WK, and we'll see that later. OP star equals X star I is the unit vector along the X direction, plus Y star J. Y star J. J is the unit vector along the Y direction. We have EP star here that we can substitute in this expression, and we can see that OP star is minus of WK, which is OE, plus W over Z, X minus X star times I, plus W over Z, Y minus Y star times J, plus W over Z, Z minus Z star times K. These last three expressions come from EP star. The X coordinate X star will be corresponding to the ith component in this equation. In other words, X star using vector algebra is OP star dotted with the unit vector along the X direction, I. Once we do that, X star equals W over Z, X minus X star. I can use this equation, rearrange it, and get my X star as W times X over Z plus W. Likewise, Y star equals OP star dotted with j. In other words, y star is the jth component in this equation, which is w over z times y minus y star. Once again, I can rearrange this equation to get my y star as w times y over z plus w. And we see that z star is 0. Continuing with perspective viewing, I can rearrange the expressions for x star and y star along the column vector in homogeneous coordinates representation. X star, y star, 0 and 1. X star is wx over z plus w. Y star is w times y over z plus w, 0 and 1. Again, in the previous lecture, we saw equivalence in homogeneous coordinates. To repeat, if I multiply this column by any scalar, it would not change the Cartesian coordinates of the point. So, if I multiply this column vector by z plus w over w, the factor z plus w over w is inverse of this factor here. Upon multiplication, I get x star here, y star in the second row, 0 in the third row, and in the fourth row, this will be z plus w, the entire thing over w, or z over w plus 1. I can represent this column vector in this form. I can extract the 4 by 4 matrix from this column vector and separate the expressions over here in terms of this 4 by 4 matrix here and the original column vector x, y, z and 1. Notice how 1 over w appears in the 4th by 3rd entry here, the 4th row and the 3rd column. In the rigid body transformations, we had seen that these 3 entries will all have 0 values. If you recall, this is because of the free vectors that we had used to derive the generic form of rigid body transformations. In perspective viewing, however, the 3 entries can be non-zero. PERS is the short form of this 4 by 4 perspective matrix. Since the I position is placed along the negative z direction, this non-zero entry here corresponds to that. W is the distance from the origin. Similar perspective projection matrices for the human eye to be on the x and y axis respectively can be obtained. For the viewpoint Ex along the negative x-axis at distance w from the origin, we have the perspective image of point P written in this form: 0, wy over x plus w, wz over x plus w, and 1. Of course, there will be a transpose here because this will be a homogeneous column vector. Notice that the perspective plane will be the yz plane. Once again, I can break this column vector into a multiplication operation between a 4 by 4 matrix and the original column vector. For the viewpoint to be along the negative y-axis at distance w from the origin, we will have P star, the perspective image of point P on the zx plane, as wx over y plus w, 0, wz over y plus w, and 1. Once again, there should be a transpose here. I have written this thing in the row form, and I can decompose this column vector into a matrix multiplication operation very similar to this. We'll have a 4 by 4 matrix pre-multiplying the original column vector. In case my viewpoint or my eye is along the negative x direction, the perspective image will be on the yz plane, and in case my eye point is along the negative y direction, my perspective plane will be the zx plane. Let's take a look at an example on perspective view. A line P1, P2 has coordinates. P1 has 4, 4, and 10, and P2 has 8, 2, 4. The observer's eye is located along the negative z direction at 0, 0, minus 4. We are interested to find the perspective projection of the line P1, P2 on the xy plane. In a sense, we are interested in finding the perspective images of all points on the line P1, P2, the image being on the xy plane. Let's say we have some position vector P1 and another point P2. These are position vectors, and we have a line joining these points. Line is L. Any point P lying on this line can be expressed in the parametric form. That is, P one minus u, this is a scalar here, times P1 vector, plus u times P2 vector. U, as I mentioned before, is a scalar or a parameter. Note that when u equals 0, P equals P1. So corresponding to u as 0, we get this point, and corresponding to u as 1, this scalar is 0, this scalar is 1. So for u equals 1, we get this point, P2, P as P2. For values of u smaller than 0, P would be lying somewhere here, and for values of u greater than 1, P will be lying somewhere here. In a sense, this relation describes point P as a linear combination of position vectors P1 and P2. We are going to be witnessing these relations quite a few times later in the course. As I explained right now on the board, any point P on a line defined by position vectors P1 and P2 can be expressed as a linear combination of two scalars. In a sense, P equals 1 minus u times P1 plus u times P2. For P to lie in between points P1 and P2, the value of the parameter should be in between 0 and 1, including both 0 and 1. If I substitute different components of P1 from here, 4, 4, and 10, and different components of P2 from here, 8, 2, 4, and then write P in component form after performing the multiplications and after also performing the additions, I get the x component of P as 4 times 1 plus u, the y component of p as 2 times 2 minus u, and the z component as 2 times 5 minus 3u. With the components of p known, we are ready to determine the perspective image of point P, which is not difficult at all. We have seen this perspective matrix before, 4 by 4 perspective matrix. We also know that our eye is positioned along the negative z direction at distance 4. So this scalar here, perspective scalar, will be 1 over 4. All the entries here will be 1. And this 4 by 4 perspective matrix will multiply different components of P, expressed as a homogeneous coordinate vector. After performing the multiplication, we see that P star has 3 components: 4 times 1 plus u in the x, 2 times 2 minus u in the y, 0 in the z, and 7 minus 3u over 2 in place of 1. Using equivalence in homogeneous coordinates, I can scale this entire vector by 2 over 7 minus 3u. Once I do that, the x coordinate is 8 times 1 plus u over 7 minus 3u. The y coordinate is 4 times 2 minus u over 7 minus 3u. The z coordinate remains 0. And this value becomes 1. I use this column vector and plot all the points for values of u between 0 and 1. We have this figure. The line in red shows the original line joining P1 and P2, and the line in blue shows the perspective image of this line in red on the xy plane. EZ is the position of the eye along the negative z direction. Notice that the projections are not parallel. They are converging to the eye from points P1 and P2. Wherever these projections intersect the xy plane, you would find a corresponding image of P1 here and of P2 here. This is how the perspective image might be thought of being constructed geometrically. Parallel projections. Parallel projections are of 3 kinds: orthographic, axonometric, and oblique. In your first year drawing classes, you must have learnt about orthographic projections and a particular case of axonometric projections, the isometric ones. Well, there are 2 other kinds of axonometric projections. They are dimetric projections and trimetric projections. Let me explain to you how to get orthographic projections in the first angle. Consider that this is the object and we would want to capture different views of this object on these 3 different planes: 1, 2, and 3. They are all perpendicular to each other. Now, I'll place the object in between you and this plane. So you're looking at the object from the front. Imagine that parallel projections are emanating from you. They are hitting the object, and imagine that the object is transparent and it is allowing all the projections to pass through itself and hit on this plane. So for you, this plane will capture the front view of this object. Let me write this down. represents the front view. Next, consider that you're looking at the top of the object. You're looking at the top view. Once again, imagine that this object is transparent. The parallel projections are emanating from you. They are hitting this object. The object is allowing those projections through itself, and the projections are hitting on this plane. In other words, this plane will capture the top view of this object. Let me write this down again. We'll have the top view of the object. Finally, the side view. Let me rotate the entire setup. Now consider that you're looking at this object from this side, from its left hand side. Again, parallel projections are emanating from you. They're hitting this object, and these projections are being allowed by the object. The projections fall on this plane. So this plane will in fact have this view, or the left hand side view of the object. Now let me unfold these planes. Observe how the three views have oriented themselves. The top plane will show the front view. The bottom plane will show the top view. And the plane to the right of the front view here will show the left hand side view of the object. This is what you know as the first angle projection. For the third angle projection, the process is very similar. Two things are different. Now again, parallel projections are coming from you. They are hitting this object, and instead of this object allowing those projections to pass through it, it is now opaque, and the projections get reflected back. Now if you imagine a plane in between you and the object, those projections are going to fall on this plane. Similar would be the case when you consider the top view and when you consider the side view. For the third angle orthographic projection, this plane here will be the front view. This plane here will be the top view, and this plane will be the left hand side. The orientations of these planes will be slightly different. If you consider my hands to be those planes, for the third angle projection, this would be my front view, this would be my top view, and the plane here will be my right hand side view. In other words, these planes get reoriented slightly differently for the third angle projection. Now this explanation is for the first angle projection. This plane here, the xy plane, it will be the top view. Imagine that the object is here and you're looking at the object from the top. The corresponding 4x4 orthographic projection matrix PR sub xy will be given by 1, 0, 0, 0, 0, 1, 0, 0. All zeros in the third row. Notice that the z coordinates will be 0, and all entries over here as 0, and the last entry being 1. Imagine now that the object is here, and you're looking at this object from this side along the negative y-axis. This plane here will be the front view. The corresponding projection matrix PR sub Zx will be given by 1, 0, 0, 0, 0, 0, 0, 0. Notice now that all the y coordinates are 0, 0, 0, 1, 0, 0, 0, 0, 1. And finally, this plane here will be the side view. The corresponding projection matrix PR sub YZ will be given by all zeros in the first row. Again, the x coordinates of all the points will be 0. And then for the second row, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Likewise, similar matrices can be extracted or derived for the third angle projection. Let's consider a very simple example. Say this is an object and we would like to have the orthographic projections, the orthographic views in the third angle scheme. This would show the front view of the object. This would show the top view of the object. And this would be the right hand side view of the object. You must have been told in your first year drawing classes that in the third angle projection, the front view is always below the top view. And in the first angle projection, it is the top view which is below the front view. Next, axonometric projections. As I mentioned earlier, isometric projections happen to be a special case of axonometric projections. The idea is quite simple. Say we have a cube, and the origin of the Cartesian space coincides with one of the vertices of this cube. All lengths are equal to 1. In a sense, this is a unit cube, and so the coordinates of this point will be 1, 0, 0. The coordinates of this point will be 0, 1, 0. And for this one here will be 0, 0, 1. The idea is quite straightforward when taking axonometric projections. You would want to rotate an object represented by this cube about any two axes. Here, we rotate this cube about the y-axis and about the x-axis. Now, the angles of rotation can be arbitrary. Here, we have the angles as phi and psi. Specifically, in this example, we rotate this cube about the y-axis counterclockwise by an angle phi, and then we rotate that result about the x-axis by an angle psi. This is again in the counterclockwise direction. And then we take the projection of the result on the xy plane. The plane formed by two orthogonal axes about which this object was originally rotated. What would be the resulting transformation matrix? Let's take a look. The transformation will be given by matrix M, a 4 by 4 matrix in size. The first matrix will be the rotation about the y-axis. You are now familiar with these terms and how to construct these rotation matrices. 1 cosine of phi minus sine of phi, sine of phi, and cosine of phi. Rotation matrix for rotation about the y-axis. Next is rotation about the x-axis. 1 cosine of psi minus sine of psi, sine of psi, cosine of psi. All the other elements remain 0 except for this 4 by 4th entry, which is 1. And this would be the projection matrix for projection on the xy plane, for which the z coordinates will be 0. We can multiply these three matrices together and get this result, a 4 by 4 matrix with these elements: cosine of phi 0, sine of phi 0, sine of phi, sine of psi, cosine of psi, minus cosine phi times sine psi 0. All entries are 0 in the third row, and then 0, 0, 0, 1. We have already said that we assume that a cube is resting at the origin with three edges of the cube coinciding with three principal axes. What the new coordinates of the three vertices would be? Well, we can use transformation. We can use this result here. So we pre-multiply the coordinates of the three vertices, namely 1, 0, 0, 0, 1, 0, 0, 0, 1. We transpose and we express these coordinates in homogeneous coordinate system. We pre-multiply this matrix by this transformation matrix. We get this result: cosine of phi, sine of phi times sine of psi 0, 1, 0, cosine of psi 0, 1, sine of phi minus cosine of phi times sine of psi 0, 1. These are the new coordinates of these points. Well, what would now be the lengths of those three edges of the cube? Let's see. We discussed this in edge foreshortening. The new lengths of those edges will be cosine squared phi plus sine squared phi times sine squared psi plus 0 squared. We know that from coordinate geometry. And since the original length of this edge was 1, the foreshortening factor SHX will be the new length over the original length, which is 1. So the new length. Correspondingly, the change in length along the y direction will be SH sub y, which will be given by cosine psi. The factor change in length along the z direction will be given by SH sub z, which will be equal to sine squared phi plus cosine squared phi times sine squared psi, right here, plus 0 squared, which does not appear here. So these three are the new lengths of the edges. These are the corresponding foreshortening factors along the three principal directions. Now, in a diametric projection, two of these factors will be equal. Noting this thing from the other side, two of these factors will not be equal. Let's take an example when the foreshortening factor along the y and along the z directions, sh sub y and sh sub z, are equal. This implies that cosine squared psi is equal to sine squared phi plus cosine squared phi times sine squared psi, which is this term. We can square this equation. Sh sub x squared equals cosine squared phi plus sine squared phi times sine squared psi. What we can do now is flip this equation and add to this equation. In other words, we are adding these two terms together and we are adding these two terms together. With some simplification, the result is given by 1 plus sine squared psi equals cosine squared psi plus sh sub x squared. This equation is expressed in terms of a free foreshortening factor, shx. Remember that we made the foreshortening factors shy equals shz. This result can be used to determine the angle psi in terms of the shortening factor along the x direction. That is, sine squared psi equals shx squared over 2, or sine psi equals plus or minus shx over square root of 2. Once we know sine psi, we can determine sine phi as plus minus shx over under root of 2 minus sh sub x squared. What we observe is, if we consider one of the foreshortening factors as a free choice, that is, if we consider shx as a free choice, we can determine both rotation angles phi and psi. Here is an example of a diametric projection. You would like to take the projections of this object. This is a view for phi equals minus 20.7 degrees and psi equals 22.21 degrees. Another view for phi equals minus 20.7 and for psi equals minus 22.21. The third one for phi equals 20.7 and psi equals 22.21, and the fourth one, phi as 20.7 and psi as minus of 22.21. Now these angles are for a specific value of shx. In the isometric projection, all factors are equal. That is, factors along the x, y, and z directions, sh sub x, sh sub y, and sh sub z, they are all equal. We can work out the mathematics using these three relations and this condition, and we'll find that the angles psi and phi attain specific values. Sin psi becomes equal to plus or minus 1 over under root of 3, which is plus or minus 35.26 degrees, and phi assumes the value of plus minus 45 degrees. If we consider these foreshortening factors, they are all equal to under root of 1 minus sine squared psi, which is equal to under root of 2 over under root of 3, which is 0.8165. An example with isometric projection. These are 4 different views corresponding to 4 different sets of angles phi and psi. Trimetric projection. Here, none of the shortening factors are equal. In other words, angles phi and psi can be chosen freely. This one is a view when phi equals 30 degrees and psi equals 45 degrees. We now come to oblique projections. When I was young, before I went into formal training, I used to draw a cube like this. I'm sure many of you would be drawing the cube in a similar fashion. When I took my first course on engineering drawing, they introduced me a scheme to draw a cube like this. We all know that this is close to an isometric view of the cube. And then I started scratching my head. Was I sketching the cube right here? It apparently turns out that I was. And in fact, this is an oblique view of the cube. Oblique projections. Parallel projectors are inclined at an angle to the plane of projection. Faces parallel to the plane of projection, in this case the xy plane, are not foreshortened. Angles between the edges of the parallel faces are also preserved. Notice these two faces on this cube. These lengths are not foreshortened, and the internal angles also remain as 90 degrees. Let's work on some mathematics on oblique projections. Say we have a point A at distance 1 from the origin along the z-axis, and say we have an inclined projection passing through this point and hitting the xy plane. This projector is hitting the xy plane at point B with coordinates b sub x, b sub y, and of course z is 0. Let's take another inclined projector parallel to the previous one. This projector passes through this point C with coordinates 0, 0, z. The projector hits the xy plane at point D with coordinates d sub x, d sub y, and 0. Once again, AB and CD are projectors at angle theta to the xy plane. This is the angle. Let me shade the triangle AOB. Let me also specify the angle BOX as psi. That is, BOX is angle psi. Let me say that the distance OB is equal to F, and let me call it a shrink factor. This distance OB is F, which is the shrink factor. It is not difficult to note that triangles AOB and COD are similar. We can use some trigonometry to determine different coordinates. B sub x, B sub y, D sub x, and D sub y. Now, B sub x is F times cosine psi. This distance is B sub x, which is the projection of OB on the x-axis. Length of OB is F. Likewise, B sub y is F sine psi. B sub y is this distance, projection of OB on the y-axis. Now, F equals cot theta. Well, we consider triangle AOB. 1 over F is tan of theta, and so we get this result. Dx is the projection of OD on the x-axis, and the distance OD can be determined using the similar triangle property. Dx, therefore, is Fz cosine of psi. Clearly, distance OD is F times z. Likewise, dy is F times z times sine of psi. Now, imagine that we would want to get or obtain the oblique image of any point P with coordinates x, y, and z. And let that oblique image be given by point Q with coordinates qx, qy, and 0. All we need to do is appropriately move point C to coincide with point P, and accordingly these coordinates dx, dy, they get changed to qx, qy with minor manipulations. Qx will be equal to x plus f times z cosine of psi. Note that this is dx, and qy equals y plus f times z sine of psi. Note that this is dy. In a sense, we add x to dx to get qx, and we add y to dy to get qy. The corresponding transformation matrix for an oblique projection will then be given by this 4 by 4 matrix here, with entries 1, 0, f times cosine psi, 0, 0, 1, f times sine psi, 0, all zeros in the third row, because z is 0 for the projection, and 3 entries as 0 in the fourth row, the last entry being 1. These will represent points in Cartesian space, and these will represent the coordinates of the corresponding oblique projections on the xy plane. Oblique projections are called cavalier for f equals 1 and cabinet for f equals 0.5. These are the two examples. This is a cabinet projection for psi equals 15 degrees, and this is a cavalier projection for psi equals 45 degrees. Notice that rectangular features which are parallel to the plane of projection are preserved, both in length as well as the internal